Welcome to GK TechVerse. Have you ever seen this error and you wonder what went wrong? In one real case, it was just a static hash map inside a Spring Singleton bean. Every request kept adding data, nothing was ever removed. And slowly, the heap kept growing until crash. Or maybe the problem too will be familiar to you. Your app starts fast and smooth within milliseconds. Then suddenly it increases response time. No error, no exception, just a freeze. That's a that's a garbage collection pausing your app. So what's really happening inside JVM? Today I will show you how Java manages memory, what the heap actually looks like, how GC decides what to clean, why your app freezes, and how to fix memory leaks. This is the knowledge that separates senior engineers from everyone else. Before we go deep, let me give you the big picture. Java, Java is not like C or C++. You don't manually allocate and free memory. The JVM does it for you. But automatic doesn't mean magic. The JVM follows very specific rules about where it puts different kinds of data, how long it keeps them, and when it cleans them up. When you understand those rules, two things happen. First, you write better code because you know what you are creating in memory and how long it stays. Second, you debug production problem very faster because when something breaks, you know exactly where to look. Let me let me show you the three things every Java process needs from memory: stack, heap, metaspace. If you see stack, each thread gets its own stack. Thread means every request is one thread. So each thread gets its own stack. And what it stores? It stores method calls, local variables, return addresses. It will not store objects. It stores only reference of that object. And the size will be fixed. Usually it is 512 KB to 1 MB per thread. Object memory, which is heap, which is shared across all threads, stores all objects, creates with new. Whenever you create new objects with a new keyword, the object will store in heap. The size will be configurable. Default will be 256 MB to 1 GB. And the class memory, which is called Metaspace, which stores class definition, method bytecode, static fields. So you need to remember, whenever JVM loads class, the all static fields will be loaded. It's all static fields are belongs to your class only. And the static fields will be shared to every thread. Like if 100 requests received, the static fields will be commonly shared to all the threads. That's why you need to very careful to declare the static fields. Let me show you the complete JVM memory map. So this is the diagram that will anchor everything else we learned today. When you start a Java application, the JVM splits up the available memory into distinct regions. Each region has a specific job. And understanding what goes where is the key to everything. Here we see stack. It is per thread. It will hold all method call frames, local variables. Heap is shared Heap memory is shared all objects, like whenever you create new objects, it will occupy the heap memory, and GC will manage this heap memory. And Metaspace, so all class metadata and static fields will be loaded. Code cache, so JIT compiled native code. And PC register, current instructions pointer per thread. The key factor you need to remember, only heap and metaspace are managed by garbage collector. Stack is auto managed via push pop at method entry and exit. Carefully observe this architecture. We will discuss more on each region like stack, heap, metaspace, how garbage collector will work. So we'll learn more in details. Just watch this architecture carefully. How Let's start with stack memory because it's the simplest to understand, and it's it's the foundation for understanding everything else. Every thread in your Java application gets its own private stack and it's not shared. It means if 10 requests means 10 threads has its own private stack. So the data inside the stack or method calls and the local variables will not be overridden because each request will have its own stack. The stack works exactly like a physical stack of plates. You add a plate on top, you remove from the top. It's like last in, first out. In Java, each plate is called a stack frame, and a new frame is pushed onto the stack every single time a method is called. Let's take let's take if your main method is calling two methods like method 1 and method 2. So method 2 is calling from method 1. Like here, method 2 frame, method 1 frame and main frame. The first exit is method 2. After that, method 1 and main method. This is the detail most people miss. A stack frame is not just a method. It contains specific things. Like it will hold the local variables like object reference, and if you declare int local variable, the local variable and the value will be stored in the stack. And if you declare any object like string name equal to new string, the object will be created in heap, but no variable and reference will be in stack. This reference is tagging to heap memory, and your intermediate method calculations will be happen. And whenever one method is calling another method, the push pop workspace will happen. And the frame data here, if you see the returns, if method exit with any return addresses, it will hold all this. So key points we need to remember: primitives in the frame, object references stored in the frame. Let me show you this with code from a real banking transaction service. Here if you see, let's example user requested for process payment. So each request is a thread and it will create its own stack frame, right? See, the first process payment method will be pushed, right? And it will have all order ID reference, stack frame object will hold all the local variables, right? Primitives will be stored in the stack frame. And here if you see, we are calling another method create payment. So then again the new stack frame will be pushed into the stack frame, right? So this is the top frame. First will exit. So once this method will exit, it will clear from the stack, and all the reference object and local variables will be stored in this frame. And also once this process payment exit, this is also will remove from the stack. One thing you need to remember, all the object will be created in heap, right? Here if you see payment object we created, This is the object which will create in heap, but the reference will be stored in stack, right? Using stack memory, we will get stack overflow error. If you don't handle stack memory, we will face stack overflow error when the stack explodes. Every stack has a fixed size. It's typically 512 KB to 1 MB per thread. If you keep pushing frames without ever popping them, for example, with infinite recursion, then stack runs out of space. Like if you're running your method in a recursive way and that is never ending, so if it is not breaking that loop, then you will face a stack overflow error because that stack runs out of space because each frame is pushing. That's a stack overflow error. And if you see this code snippet here, we are calling validate order recursively, right? If the condition is not breaking, so it will continues the loop, and the result you will get stack overflow error. Each call pushes a new frame. So stacks fills up and then it will blast. So you have to handle the code properly. Now we'll talk about heap memory. The heap is the largest and most important region of JVM memory. Everything you create with new ends up here. But the heap is not one big flat bucket. The JVM divides into generations. The whole idea is simple. Most objects in Java die young. Only a few live longer. And the JVM is designed around this behavior. Think about it. In a web application, you create a request object, process it, return the response. That request object is dead within milliseconds. You also create a user session object. It might live for 30 minutes. Having one heap would mean the garbage collector has to search through all objects, including that session object, every time it wants to collect the dead request objects. Generational GC solves this by separating short-lived objects from long-lived ones. Now the GC can collect short-lived objects very fast without touching the long-lived ones. The young generation, where most objects are born and die. The young generation has three subspaces: hidden, hidden, survivor, and survivor 1. When you create a new object with new, it always starts in hidden. When hidden fills up, a minor GC runs. It scans hidden, collects all dead objects and moves the surviving ones to survivor. On the next minor GC, the survivors from both hidden and S0 are moved to S1. S0 is cleared. They alternate S0 to S1, S1 to S0. Like a ping pong match. Every time an object survives a GC runs, its age counter increments. When an object reaches the age threshold, default is 15, it gets promoted to old generation. Here if you see, young generation will have hidden space, survivor 0, survivor 1, right? In old generation, it is basically the long-lived objects. Old generation holds objects that have survived many GC cycles. Typically, in a Spring Boot application, your singleton Spring Beans, your database connection pools, your caches, these all end up in old generation because they live for the lifetime of the application. Old generation is larger than young generation. A major GC runs when old generation fills up. Major GC is much slower than minor GC. It has to scan a larger space. And here is the critical concept. A full GC scans everything, young generation, old generation, and metaspace. This is the most expensive operation in JVM. In production systems, full GC passes or what cause freezes. The application stops responding for hundreds of milliseconds or even seconds. You understood now, right? When full GC scans everything, like young generation, old generation, and metaspace, then it will pass the application. That's where you will see the slowdown of your application. Here we can see what ends up in old generation. Like your Spring Singleton Beans lives for app lifetime, right? So it will be in old generation. And if you created any cache like this cache, if it grows, goes to old generation and stays there. Now from here code snippet, we can see what ends up in old generation. Okay, so in Spring Singleton Beans lives for app lifetime, right? So it will be in old generation. And this cache, if you see this product cache, if it grows, it will go to the old generation and stays there. And connection pool managed by Hickory pool, objects in old generation. And this method, if you see here, the product object starts in Eden. So whenever the product object created, it starts in Eden. If product cache grows, then will be a memory leak. Here we observe if this product cache increases, let's say, if cache never evicts, the memory leak issues will happen. So make sure you have to keep bounded and you can evict the data. Here we now we'll talk about Metaspace memory area. Before Java 8, there was a region called permgen. It is permanent generation. Permgen stored class metadata, interim strings, and static variables. Permgen had a fixed maximum size, which is typically 64 MB to 256 MB. When you deployed too many classes, or when frameworks generated a lot of classes at runtime, and Hibernate, Spring, you would get Java out of memory permgen space. Every Java developer from the Java 6 or 7 version has been burned by this. In Java 8, Oracle completely removed permgen and replaced it with Metaspace. The key difference, Metaspace lives in native memory outside the JVM heap. It's part of the operating system's memory, not the heap you configure with XMX JVM flag. And by default, Metaspace grows dynamically, no fixed limit. This eliminated most permgen out of memory error issues. Now we'll walk through the garbage collection, how it really works. Garbage collection is the most misunderstood part of JVM memory and the most asked about in senior interviews. Let me be very clear about something first. You cannot force garbage collector. You can call system.gc, but it's just a hint. The JVM decides when to collect. Garbage collector works in three phases: mark, sweep, and compact. Let me walk you through each one. The GC routes, where the scan begins. The GC cannot just scan every object on the heap. That would be impossibly slow. Instead, it starts from a fixed set of anchor points called GC routes. These are objects that are definitely alive. From each GC route, the GC follows references like tracing a web and marks every reachable object as alive. Everything not reachable from a GC route is dead and eligible for collection. This is why static hash map was a memory leak. In our production incident, when we declare static hash map, that was a memory leak. A static field is a GC root. The hash map was always reachable. The objects inside it could be never be collected. Now in step 2, sweep and compact. After the mark phase, the garbage collector already knows which objects are alive and which are dead. Now comes the sweep phase. The GC removes all the dead objects. Their memory is freed. But here is the problem. Memory is now scattered. You get small empty gaps between live objects. We call this fragmentation. To fix this comes compact phase. The GC moves all live objects closer together. This removes all those gaps and creates big one big free space. Now memory allocation becomes super fast, just a simple pointer move. But important point, not all garbage collectors do compaction. And this is a key difference between GC algorithms. In modern JVM offers multiple GC algorithms, each makes different trade-offs between throughput and pause time. In Java 9 plus, G1 GC becomes the default, and Java 15 plus GCC become production ready. Choosing the right one for your application is senior level skill. So now we'll talk about memory leaks which cause the production issues. A memory leak in Java is not about forgetting to free memory. The GC handles that. A Java memory leak is when objects are no longer needed by your application, but your code still holds a reference to them. Because there is a reference, the GC sees them as a live and refuses to collect them. The heap grows eventually and out of memory error will get. I have seen 5 patterns cause 90% of production memory leaks in enterprise Java. Let me walk you through each one. The first pattern, if you see, static collection. This is like most common issue. Here in this code, we have created a static session. Every session added and none of them removed. And eventually it will grows. Then it cause out of memory error. The best way to use, we have to create a bounded cache. Like we have to create a TTL. You have to set the expiry time. Here we have created a static session. It's a map. So we are pushing all the sessions added to this map and none of them removed, right? So this will grows and we can get a out of memory error, right? So instead of that, the best way to we have to keep the maximum size. So you have to set TTL, then auto evict idle sessions. Second pattern, if you see, unclosed resources. Let's take this example. So there is a database connection you have used and you are not closed. Like no, when you get any exception, this close method will not reach, right? So this can cause out of memory error. So instead of that, we have to use try with resource. So it will take care of automatically closing the connections. The third pattern is ThreadLocal variables not removed. Like when you are using ThreadLocal and you forgot to remove it, then you will have the out of memory issue. So the best way to, you always, when you are using ThreadLocal, you always clear that. Like you have to, in finally method, you have to clear that pattern. Like whenever you use in Spring Boot application, when you are using event listeners and you are not deregistered, that time also you will get the out of memory error. Like you have to remove it. When you subscribe, you have to do unsubscribe, right? The another pattern, like in the fifth case, like it is incorrect equals and hash code in collection, like no hash map or hash set when you're using without no overriding equals and hash code, then what will happen? So the duplicate keys will get inserted and the data will grow. So that time also you will get the out of memory error. So these are the five most frequently we we face this out of memory error. Now you know what causes memory leaks. Let me show you how to find them in production. Like we can use VisualVM is a free tool which included within JDK. Like if you are using Java 8, before Java 8, it is part of your JDK. Like you can find it in installed JDK path in bin folder. There will be a VisualVM. You can open and whenever you run the application, so it will clearly show you the heap memory and the other Metaspace related information. It is the fastest way to take a heap dump and analyze it. So these are the steps you can follow. All right, pause after each question and try answering yourself first. These are real questions from senior Java interviews at product companies and MNCs. If you can answer all nine confidently, you are ready for any JVM memory questions at any company. Now we'll close the session. Let's bring everything together. This is the cheat sheet you need to have burned into your memory before any Java interview. I'm going to I'm going to show you the complete summary on screen. Keep this open and refer to refer to it anytime. If you like this video, please hit like and subscribe. Drop a comment. Thanks for watching GK TechVerse. Subscribe and keep upgrading your skills. See you in the next video.